I'm Sonali. I'm a postdoc in the A&D department. Welcome to the 4th day first session of Showcasing RRI. Our first speaker is Professor Biswajit Paul from Astronomy and Astrophysics department. He works on various aspects of high energy astrophysics, compact stars, X-ray binaries, and polarization measurements. And today he will tell us about the highs and lows of accreting neutron stars.
So, I would be talking about timing and spectroscopic studies that we do of neutron stars, primarily neutron stars which are in binary systems, and they are powered by accretion of material from a companion star by various mechanisms. This is what we have been doing over the years, and then I would talk about what we plan to do in the coming years with an instrument that we are building at RRI. So, some details about the instrument and the kind of science that we plan to do with this instrument. So, let me start with an admission that we do not work on, unlike many of my colleagues in Astro and other groups at RRI, we do not work on grand problems in astrophysics like when the first stars were born, when how does the galactic outflows control evolution of galaxies and enrichment of the universe, or quantizing gravity. We work on individual objects, trying to understand them better, and at times this leads to better understanding of the class of objects that they belong to, or at times it has led to our questioning what was the general belief about that class of sources. So that's more or less our theme. And over the years, while working on these objects, we have had some surprising results. So some of those are still puzzles for us. So I would be briefly mentioning those as well. Now, X-ray binaries, especially neutron stars in X-ray binaries, come in different varieties. The main classification is based on what is the type of the companion star. Okay, so these are low mass X-ray binaries where you have a neutron star with a low mass star as a companion, typically less than 1 solar mass. In these kind of objects, the mass transfer from the companion to the compact star happens by what is called Roche-Loeb overflow. It's basically the neutron star drawing out material from the companion. Okay, black holes are also found in this kind of systems. Here, much of the matter that is taken out from the companion is accreted onto the star. If you have a high mass star as a companion, like a 10 solar mass star, as Biman told the other day, a high mass star is far more luminous. Okay, the mass to luminosity relation is something like L to the power 3. So 10 solar mass star is 1000 times more luminous, and it's hotter also. It has a lot of ultraviolet radiation. Because of this ultraviolet radiation, it interacts with the outer layer. These more massive stars are always blowing away their outer layer. They are always shedding mass. Okay, and the mass shedding rate could be quite high, of the order of 10 to the power minus 6 solar mass a year. Okay, and so on. This wind outflow is in all directions. A tiny part of that, typically about 1,000th of that, could be captured by the companion star. Captured by the compact star, the neutron star, and it could emit in X-rays. In these systems, the neutron star can outshine the companion by factor of many, like even 100. In these systems, the X-ray source could be very bright, but accretion disk is not bright enough. If you want to see this in optical, you would primarily see the companion star. In these objects, when they are bright, you would primarily see the accretion disk in optical. X-ray emission is because of the accretion onto the star. Most of the X-ray emission from a region very close to the star.
I see. Okay. So as it's infalling.
Just a second. Yeah.
As it's infalling. So at the point of infall is when the X-ray emission happens.
As the material goes in, it becomes hotter. It is it's kinetic energy getting the gravitational potential energy getting converted to kinetic energy. It becomes hotter and hotter. In case of, I will say something more about it in the next slide. Then there is another class of high mass X-ray binaries where it comes from their evolution. This star to begin with was more massive than the other one. Okay, this star during its a massive star evolves faster. Okay. So, during its evolutionary phase, this star has transferred certain amount of material onto this, spinning it up. Okay. So, this is an ordinary star, but spinning at a very rapid rate. So, at the evolution of the more massive stars, it has left behind a neutron star in an elliptical orbit. But the companion star here is peculiar in a sense that it's very rapidly spinning, so it has an outflowing disk. Instead of a symmetric isotropic outflow, which is most high mass stars have, this class of stars actually have an outflowing disk. And this neutron star in a highly elliptical orbit, whenever it cuts this disk, it captures certain amount of material and produces X-rays. So these are the three varieties of sources that we mainly study.
All you is the fact that you have, suppose one was agnostic about what this compact object was, is the main feature that it has a very strong gravitational field and that's why it's accreting on and creating X-ray emission, or is it, I mean, really necessary to know that it's a neutron star and maybe not some other exotic object?
Two things. One is some of these objects show very rapid intensity variation. For example, the first evidence seen in the first known black hole candidate in our galaxy, Cygnus X1. If you see intensity variation at a short time scale, then the size of the object cannot be larger than the light travel time for the duration. Okay. That was the primary reason to think that these objects are compact. And being compact is the most efficient way of converting mass to energy. Right. And then seeing the pulsation in the neutron star, and at times we also measure how the pulsation rate increases. So a neutron star can be spun up very rapidly. Okay, a white dwarf or a more massive, a larger object, because it has larger angular momentum, cannot be spun up very rapidly. So neutron star with small angular momentum is easier to spin up. So seeing rapid spin up is another reason to believe that these are very compact objects. So pulsation, rapid spin up, fast variation, conversion of mass to energy, and so on. So various arguments go in favor of these being compact objects.
But these being compact, but I mean, they could be some, whether it's a neutron star or it's a black hole or it's some strange star or any compact.
Okay, so in my talk, I'm not making distinction between whether it's a neutron star or a stranger star or something. Right. It's a compact star with strong magnetic field.
That's all I
Yeah.
This X-ray studies, because the timing, the pulsar timing and all is separate from
No, this is pulsar timing in X-rays.
Oh, I see.
So these objects are not radio pulsars, and radio pulsars do not spin up at the rate that these objects do. So therefore, these are accretion driven.
Okay, so the fact that they are pulsating at some regular frequency at a very that's another evidence from this X-ray
Yes,
that it
yes,
is a
yes.
violent.
And as far as compact objects are concerned, astrophysically these are the viable ones: black hole, neutron star, and white dwarf. And within neutron star, there could be variation of how much of strange matter composition is there, and so on and so forth. And as far as the magnetic field strength go, they also come in sort of three varieties: the low magnetic field systems, millisecond pulsars, which have lost their magnetic field over a very long period of time. These high magnetic field neutron stars, which are relatively young, few 100 million years at most. And then there are magnetars. Magnetars are relatively less known as of as far as their history goes, but they are also very young objects. Okay, so now what happens very close to a neutron star if it has very strong magnetic field? The strong magnetic field stop matter to approach the neutron star directly because this matter is ionized. Okay, then they would start following the magnetic field lines and fall onto the polar cap regions. And near the polar cap regions, this material will be mildly relativistic with a temperature of about tens of kiloelectron volt. So then surface thermal photons would get inverse Compton scattered from this accreting material and produce X-rays. So these objects, when in the early days, the observations are primarily limited to about 2 to 10 kV band, and one saw a Polex shape spectrum.
You told that neutron star lose magnetic field, I mean whatever strength is going down, but if it is accreting material, then how it loses?
Neutron star magnetic field evolution is a completely different topic. Let me not get into that. Neither am I an expert on that. During the accretion phase, the people talk about field burial. Okay, that's a topic that Dipankar pursued with great success. I would not be talking about neutron star field evolution. How does it happen? So in the 2 to 10 kV band, it primarily has a power law. with better and better instruments, when we started covering higher energy band, we saw that this power law doesn't extend all the way. There is an exponential cutoff, and that cutoff is related to the electron temperature in the accretion column. Then as you go to lower and lower energy, you start seeing something beyond the power law. Okay, for example, the soft X-rays, which is reprocessed emission of these X-rays from the inner accretion disk, because these X-rays will not only come to us, it might also hit the inner accretion disk. Though the inner accretion disk in these systems is at a distance of about 800 to 1000 kilometers, it's not hot enough by itself to emit X-rays, but since it receives so much of intense X-rays, it can get heated by the X-ray radiation and can produce X-rays. So in the X-ray spectrum, you would see a power law with high energy cutoff. You can see some soft X-rays, and if your instrument has good enough resolution, this is not a spectrum with good resolution, it's a very modest resolution, you start seeing bumps on that. Like this is iron emission line at 6.4 kilo electron volt. Iron is abundant, iron has very high fluorescence yield. So if there is iron atom, all the higher energy X-rays interacting with those iron atoms would produce fluorescence, and that fluorescence is a very fluorescence line is a very useful tool for other studies that I would come to. And sometimes from the same iron atoms, you can see a bunch of lines at lower energy as well. These are K shell electrons. These could be L shell electrons in the iron atoms. So typical X-ray spectrum of this kind of a source has multiple components. Okay, and some of it is directly from the neutron star. Some of these are reprocessed emission. The reprocessing is a theme that I will keep coming back to in my talk. So why this title? Highs and lows of accreting neutron stars. Most of our studies are done by looking at the variability of these sources. Okay, which could be in the form of a flare, a burst, depending on the the shape and type and duration and enhancement in luminosity. We call this, give these different names. Could be flares, could be thermonuclear bursts, could be outbursts, and so on. And sometimes we also study eclipses and dips in the light curves of these sources. And eclipses are a very useful tool for study of these objects. I would be giving more details later. And these flares in the light curve are what are called thermonuclear X-ray bursts, which happens on low magnetic field neutron stars. The infalling material can remain on the surface of the neutron star. It will give out its gravitational potential energy. But after a lot of material is accreted on the surface, because of very high density and pressure, there could be thermonuclear fusion may start, and that would kind of lead to burning of the entire material, entire surface of the neutron star in a short span of time, of about a second or so. Then it will cool down. If all material is not burnt in one shot for some reason that is not very clearly understood, you can have repeated bursts and so on. There is a great deal of detail in these sources. In one kind of sources, what you see is that the flare of the burst is proportional to the material which is accumulated since the previous burst. Okay, that means all the material that got deposited is used up in the flare. In certain other kind of sources, what you see is that the amount of flare that is deposited is used up. So in one flare, certain amount of material gets used up, okay, and it waits for the next outburst until that amount is refilled. So various kinds of correlations are seen between duration, luminosity, etc. of the bursts. Bursts are not our prime topic for study. I would be talking about other kinds of variabilities.
Just a comment, I mean, these bursts would help you to distinguish between neutron stars and black holes, right?
Sure.
Right. There won't be any hard surface in a black hole.
Thermonuclear bursts are only seen in neutron star surface, and this is typically their intensity profile. We study various other kinds of flares and variations on accreting neutron stars. I would be talking about those.
Period is constant or
No.
It's
So by highs and lows of accreting neutron star in intensity, we mean these flares or dips or eclipses. And there are highs and lows in spectrum as well. Again, the same spectrum. You can see atomic emission lines. Sometimes, if the radiation is coming through, for example, an outflowing wind from the star or so on, then you might see absorption lines. And interstellar or circumbinary material will also absorb, the incoming radiation by photoelectric absorption, and that effect is more dominant in the low energies. For example, this power law has a turnover here. This turnover is related to how much of material is there in the line of sight. Okay, and we usually express that in terms of equivalent hydrogen column density. but it's usually the oxygen and carbon in the line of sight which causes most of the absorption, or iron. And depending on how much of absorption is there, absorption may even start, how much of material is there in the line of sight, absorption may even start at much higher energy. So sometimes you can have spectrum like this. Okay, and certain class of agents show very strong line of sight absorption. Then you may or may not have noticed that the high energy in the high energy band, this power law, I said that it has an exponential cutoff, but there seems to be something more than an exponential cutoff. Okay, there is actually a dip in the spectrum here that comes out from detailed analysis, and that is cyclotron resonance scattering feature. On the in the accretion column where these high energy photons are produced, okay, there are electrons moving around in the around the magnetic field lines, and those electrons resonantly scatter the high energy radiation which is produced there itself. Okay, and that causes absorption dips, and these absorption dips are the only direct way of measuring magnetic field strength of neutron stars. So we study cyclotron resonance scattering feature for various reasons. So the overall themes that we have been working on in accretion powered neutron stars over the years are of this kind. We study quasi-periodic oscillations. Pulsation itself is not a big deal. Okay, if it's a neutron star rotating, it will give pulsation. Okay, pulsation itself is not so much of interest. It's intensity variations beyond pulsations which are of interest to us. We see an interesting feature called quasi-periodic oscillation. I think about 3-4 months ago we had a detailed talk by Ranjib Misra on quasi-periodic oscillations, but those are quasi-periodic oscillations in black hole sources. Our interest is primarily quasi-periodic oscillations in accreting neutron stars. A major theme that we work on is X-ray reprocessing. The X-rays which are originated onto the neutron star, other than coming to us, okay, may get reprocessed in the accretion disk, on the surface of the companion star, in the outflowing wind, and so on. Okay, many such reprocessing features is what we study in detail. Another topic that has been of interest for a long time is orbital evolution, because binary stars evolve differently from isolated single stars. Okay, very differently. Sometimes they get strongly influenced by mass transfer from the companion star, change in angular momentum because of mass transfer, and so on. So orbital evolution, therefore, has been a major theme for us, which you do using two different techniques. I will be talking about that. One is using the pulsar. Pulsar itself, when the pulsar is going around the companion star, that can be used as a clock, okay, to study the orbital parameters and evolution of the orbit. And some of the low mass X-ray binaries which are eclipsing, we use the eclipse as a tag to study the orbital evolution. Cyclotron resonance scattering feature I already said. Many of these sources go through outbursts. Many of these sources have some unique feature called super orbital intensity variation, because pulsation is easily understood. Orbital intensity modulation is easily understood. Eclipses can be seen in some cases if the orbit of the binary is along our line of sight. But then there are other very clear intensity variations in these sources which are relatively more difficult to understand. One of them is called superorbital intensity variation. We also study some of these binaries in a unique way to understand their population. For example, the X-ray luminosity function of X-ray binaries and so on. And recently we have taken up a project on a study of X-ray pulsars which are among the ultraluminous X-ray sources. These X-ray sources with a with a compact object mass of about 1.4 solar mass, that's the typical mass of a neutron star, can have a luminosity only of about few times 10 to 38 arcs per second. Beyond that, the X-ray luminosity itself will blow away any infalling material, okay, just by the radiation pressure. That's the Eddington limit for a compact star, Eddington limit for any star. But there are many sources which are seen in other galaxies, whose intensity are several times larger than the Eddington luminosity, maybe even 100 times larger than Eddington luminosity, and some of those sources are pulsars. And when you have a pulsar, it must be a neutron star. So how do we have ultraluminous X-ray sources with neutron star as the accretor in them? Okay, so we have taken up some study of ultraluminous X-ray sources, which are also X-ray pulsars. We sort of use data from any observatory which is available. We have no bias towards it, no prejudice towards it. AstroSat, NewStar, Suzaku is a Japanese observatory, NewStar is a NASA observatory, XMM Newton is a European observatory, Chandra X-ray observatory is NASA's, RXT was NASA observatory, Swift X observatory is NASA, Integral is European, ASCA is Japanese, BEPOSEX was Italian, Dutch Italian, and MAXI is a Japanese instrument on the International Space Station. Okay. We use data from whichever observatory fits into our program. So the first thing is quasi-periodic oscillation. Quasi-periodic oscillation is something which is usually not clearly seen in a light curve. If you see the intensity profile of a source, the flares, eclipses, if the source is bright, pulsations, etc., very clearly come out. What you do not see clearly in the light curve are some other subtle features. So if you make a power density spectrum of this, basically some form of Fourier transform, you start seeing excess power in some frequency. Okay. This is due to pulsation in the source and its harmonics. This is a feature which is quasi-periodic oscillation. So that's an underlying intensity variation of small amplitude, but not at a fixed frequency. It is over a range of frequency. That we believe happens because there is some inhomogeneity or intensity, density fluctuation in the accretion disk. There are many reasons why such things can happen, which may either absorb the X-rays periodically if it's a fluffed accretion disk, which can periodically absorb the X-rays, or which can modulate the mass accretion rate that is going on to the neutron star at a bit frequency. Okay, neither of these cases, it might produce a quasi-periodic oscillation feature like this. And now this is the area where we have been very successful. There are about 20 odd sources with known quasi-periodic oscillation feature among the accretion powered X-ray pulsar, and more than half of them actually have been discovered by us over the years. At times, we have used the quasi-periodic oscillations to bring out some hidden nature of these sources. For example, in some X-ray binaries, you see very large intensity variation. Okay, you might believe that the intensity variation is because of changing accretion rate onto the star. Okay, but then you look into detailed features of these sources, what you find is that over a large range of accretion rate, over a large range of X-ray luminosity, the quasi-periodic oscillation feature remains same. Okay, and if these QPOs are happening because of the inhomogeneities in the inner accretion disk, then the inner accretion disk radius defines what the quasi-periodic oscillation is, frequency is. Okay, and the inner accretion disk radius is decided by the magnetic field strength and mass accretion rate. Okay, so even though the X-ray luminosity appears to be vastly different, the underlying mass accretion rate probably remains same in these sources, and which is brought out by the constancy of the quasi-periodic oscillation frequency. So you use QPOs for various things. Sometimes if you do not see cyclotron line from a source, these quasi-periodic oscillation frequency can be used to indirectly infer the magnetic field strength, not very accurately, within factor of a few. The other major theme is X-ray reprocessing. So this is very natural that if you have a lot of X-rays being produced from a region close to the compact star, these X-rays would outshine or shine everything around it. Reprocessed X-rays, mainly in the form of emission lines of iron and other atoms, would be seen from the accretion disk, from the environment of the neutron star, even from the surface of the companion star. And we use that efficiently. I already told you about this feature, that in some cases in X-ray pulsars, in addition to the power law component, we see a soft X-rays with a black body temperature of about 0.1 kilo electron volt or so. So that is one type of X-ray reprocessing. The hard X-rays causing heating of the inner accretion disk, thereby producing soft X-rays. And the pulsation feature of the hard X-ray component and the soft X-ray component in these sources are different. One other way of using studying let's skip this, the X-ray processing in these systems is, when the neutron star is visible to us, we are seeing a large amount of emission from the neutron star, and maybe about 1% reprocessed emission from the from the environment. It is difficult to study the reprocessing features in detail in presence of this continuum. Then what we can do is look at those sources which have eclipses, that is their binary plane is along our line of sight, and if we compare the X-ray spectrum of these sources when the neutron star is directly visible versus when the neutron star is blocked by the companion, all that you see is reprocessed emission. And therefore what comes out is, in the reprocessed emission you see a predominance of an iron line. Okay. So, we use Eclipse spectrum of these sources and compare that with out of Eclipse spectrum to understand the reprocessing environment in these kind of systems. Another way of studying reprocessing is not only look for emission during the eclipse, look for emission which is in the form of a flare during eclipse. So, during eclipse whatever emission you see, this red spectrum, it can come as a reprocessed emission from the environment, or there could be another component of emission which is there all the time. For example, in a Hamas X-ray binary, the outflowing wind and some structures which are formed in the outflowing wind because of motion of the neutron star, there is collision between them. So, there are shock fronts generated. There could be X-ray emission from the shock fronts. So, when the main X-ray spectrum is blocked, the shock front need not necessarily be blocked because that is not near the neutron star. Okay. So, study of the X-ray spectrum, the whole X-ray spectrum and flares in them, therefore allow us to distinguish between multiple features of emission components in these systems. So, while we study these Hamas X-ray binaries, one class of sources among Hamas X-ray binaries that became very prominent in last 10 years or so are called supergiant first X-ray transients. Don't go by the name. What we have is, when you make optical observation, we know the nature of the companion star. It's a massive star. We look at the X-ray emission. If you compare about 30-40 sources with this kind of companion star, you find there is one class of sources which are always X-ray bright, and there is one class of sources which are usually about 4 orders of magnitude fainter. Occasionally they become bright. What causes that one doesn't know. Okay, but we took up a study of these sources in their reprocessed X-ray emission. They basically investigated the equivalent width of the iron line, how prominent the iron line is versus what is the absorption column density. If you measure the X-ray spectrum, the absorption column density gives you a clue about how much of reprocessing material is surrounding it, okay, and equivalent width gives you a measure of the amount of light getting reprocessed by this intervening material. Okay, so these two is expected to fall in a line. What you find interesting is that this general class of sources, supergiant first X-ray transients, which are much fainter usually, they have a much smaller equivalent width compared to the other sources. Okay. What does this indicate? Probably, and it's not very clear, but probably the clue for why these sources are much fainter lies in their wind. That they probably have a different elemental abundance. Okay. The iron is probably far less dominant in these sources. One other reason one other thing people thought about these sources SFXTs, which are much fainter, usually much fainter, is that maybe they are in a wider orbit. Sometimes it's not easy to measure the orbital period of a system. Maybe they are in a much wider orbit. And we have actually discovered the orbital period in one of these systems, and that happened to be the smallest orbital period known among all SFXTs. Okay, that's a work that actually stands out in study of SFXTs. It has a period of only about 3.3 days, which makes them very similar to all other Hamas X-ray binaries. Okay, so the orbital period is not the clue for SFXTs being different from other supergiant companion stars. The clue probably lies in their wind outflow. That's what has come from study of reprocessing in this class of sources, SFXTs. Here is another source. Sometimes study of individual sources tell us a lot. Here is one source where we have measured, or people have measured, the pulsation as the neutron star is going around the companion, and from pulse arrival time you can determine the orbit, its orientation with respect to our line of sight. What is found in this source, which is most peculiar, is that the X-ray intensity of this source shows a very periodic modulation and a flare in every binary orbit. The binary orbit period is about 40 days. Okay. What is most interesting is this phase 1 is when the neutron star is closest to the companion in its orbital motion. So you would expect a flare and X-ray intensity to go up when the neutron star is closest to the companion, right? That is when it can accrete most amount of material, or maybe a little later, because the accretion capture has happened. It takes a little time for the matter to fall onto the neutron star. You would have expected a flare aligning with this phase 1, or maybe a little later. The most surprising thing in this source is it shows an X-ray flare which is little earlier than this. Yeah. That's there in another slide. I will talk about it little later in a different context though. Okay, so people have given 2-3 different models trying to explain this, but those models have certain predictions also. Okay, predictions of this material which is getting accreted onto the neutron star, what is its distribution in the binary system, and that distribution should be detectable in its reprocessing of X-rays. That material which is causing this flare should also cause reprocessing of the X-rays, and then there are models of how the absorption column density and how the strength of the iron line in its binary orbital phase should evolve. And we went out to make these measurements, and it turns out to be very, very different from the existing models for these sources. Okay. So, simple-minded model, it looks like do not work for many sources if you look at them in detail. And I would like to point out here is that for this particular study, we have used data from a satellite from an instrument called MAXI, which is on the International Space Station. That's an all-sky X-ray monitor, not meant for this kind of spectroscopic study. Okay. So these are the cases where we have gone and sort of invented new ways of looking into X-ray data that is publicly available. These kind of studies have not been done even by the instrument team which made the instrument. The X-ray reprocessing happens not only in the X-ray band, it can also happen in optical band. So if you have simultaneous X-ray and optical measurement, there are interesting things to do. For example, the thermonuclear X-ray burst that I mentioned in the very beginning. Okay. Thermonuclear X-ray burst happens on the surface of neutron star. The X-ray intensity rises in a fraction of the order of a second or so, and then it falls typically in 10 to 30 seconds duration. In all of these panels, the bottom figure is that of a thermonuclear X-ray burst. Okay, this study is done with the XMM Newton Observatory, which along with the X-ray instrument also has an relatively modest optical instrument. So simultaneous with every X-ray outburst, X-ray burst of this kind, there is an optical burst also, which is probably happening because of reprocessing of these X-rays from the accretion disk, the material that is falling onto the neutron star. What is surprising here is that the relative intensity between the X-ray and optical is variable. As you can see, like this is a very weak reprocessing compared to this one, which is much stronger. Yeah.
What exactly is the reprocessing? So you've got X-rays, and then you've got a secondary mechanism by which.
So it could be 3 things. One is the X-ray can cause heating, and that heated material can have thermal emission. That is probably the case here. X-ray is causing heating of the accretion disk, which is then re-emitted in optical or ultraviolet. Okay. In case of X-ray emission, it could be fluorescence emission from the iron lines or other atoms in the same material, or it could be X-ray scattering, Thomson scattering. So in the Eclipse spectrum that I showed, there is a continuum. That continuum part is Thomson scattering. The line that you see is fluorescence emission, and this is thermal re-emission. Okay. So here you have an X-ray flare on the neutron star, which is getting reprocessed from the accretion disk into optical band. What is surprising is that from burst to burst, you can see it's like these 2 bursts. From the X-ray to optical, there is a significant delay of several seconds, okay, which is in fact larger than the size of the binary. There is several seconds delay between the X-ray and optical, and that is larger than the size of the binary itself. Okay. And first thing to admit here is we do not understand what causes this. How can you have a significant delay from X-ray to optical? Because the thermal emission production should happen immediately, as you can see in some other bursts. The heating and resulting thermal emission should happen immediately. So X-ray to optical reprocessing is one kind of study here, and another study. This was very peculiar in Gayatri's thesis. Here we have a central X-ray pulsar, which has some 7 seconds pulse period. The pulse X-ray emission comes to us directly. We looked at the reprocessed optical emission in this source, because not many sources are suitable for optical study. If the component star is massive, then that dominates the optical emission. Like if you want to study reprocessing, you have to choose sources suitably so that the accretion disk dominates the optical emission. Here, over few hours of observation in a night, what we found is that the X-ray pulsation, of course, remains at a fixed frequency, because that is the underlying spin period of the neutron star. But over a few hours, we found the optical reprocessing period to have changed significantly. Okay. There is no clear explanation for this. Only thing that you can think of is optical reprocessing is happening because of some structures in the accretion disk. Okay. There are other evidence of there being structures on the accretion disk, and this structure is probably moving inward. That would make the spin period to appear faster. Okay, the optical period to appear faster. So these are ways of studying reprocessing.
How do you subtract the main spectrum and then you know?
No, this is not a spectral study. This is just timing. So the emission from the accretion disk, thermal emission from the accretion disk itself should not have any periodicity in this. Whereas the X-ray irradiation that is heating the accretion disk has an underlying period. So whatever you see a pulsed emission in the optical is reprocessed emission. Rest of it is unpulsed emission, true thermal emission from the accretion disk. No, the accretion disk size is not so large. That could be tens of milliseconds maybe.
And this optical emission happening at a very large delay and with also this different timing, it could be also happening from some structure which is outside this binary system. Is that possible?
Outside binary having something which subtends a significantly large solid angle, that is unlikely.
Because you have to account for the intensity.
Yeah.
You talked about this eclipsing, right? And that there was a difference between when this thing was in eclipse and when it wasn't. And
that is one kind of study of eclipse spectrum of these sources. And what I was talking just now is optical reprocessing. X-ray.
But I thought you had said that you got an idea of the reprocessed stuff when you compared the eclipse situation with a situation where but you're saying that there are other ways to infer what is the reprocessed.
Yes, so reprocessing, seeing the reprocessing in optical tells you something, seeing the reprocessing in X-ray tells you something else, and so on. Different aspects of the same thing. Other kind of study that we have invested a lot of time and over many years. This is a topic that needs patience. Is study of orbital evolution of these systems. There are two primary ways of studying orbital evolution. One is when you have a pulsar. The pulsar is going in its binary. Okay. So if you can measure the arrival time of every pulse, okay, and take out the linear component from it, the pulse arrival should show a periodic delay. Okay, that's called pulse arrival time delay, which is basically measure of the size of the binary orbit along our line of sight. Okay, the perpendicular component cannot be seen. Along our line of sight, there will be orbital pulse delays. This can be measured very accurately. Okay, and for example, this is the pulsar. This is not a pulse. This is every pulse. How the pulse has been delayed with respect to reference, okay, and that can be measured very accurately. And this is the period when the neutron star is eclipsed by the companion, so you don't have any measurement there. So you can fit an appropriate function and determine the orbital parameters from this, okay, along with an constant component for the inclination of the orbit, a sin I factor. And if you keep doing these measurements again and again, okay, over many tens of years. Okay, it's not easy to get such extensive data. For example, it's a continuous observation of a source for about 4 days, okay, 2 binary orbits. It's not easy to get that kind of data, but every now and then you can manage or look at archival data. You have multiple measurements of the epoch of the binary. Let us say when the system is farthest away from us, when the neutron star is farthest away from us, and line them up. They should line up in a linear form. Any deviation from linearity would tell you that the orbit is evolving. So that is done using pulse timing, or in some cases, if the neutron star is not a pulsar, but still it's an eclipsing binary, then you can use the eclipse timing. Okay, and in low mass X-ray binaries, the eclipse can be extremely sharp. Okay, like few seconds to go to eclipse and few seconds to come out. Then you can determine the middle of this eclipse with very high precision of a few seconds. And if you keep doing it year after year, you would be able to line them up and then take out the linear component. You would be able to study how the orbit is evolving. So we have done this for a large number of high mass X-ray binaries, combining with data that we analyzed with earlier measurements and so on. And in many sources, you find that there is a negative component, and that is a measure of how the orbit is decaying. Yes, Shweta.
So in the previous slide, how can an accreting neutron star not be a pulsar?
If it's a low magnetic neutron star, low magnetic field neutron star, then the matter goes all the way to the surface. Like if you have magnetic field strength about 10 to the power 8 Gauss, it may not be a pulsar. So we measure the orbital evolution of these systems, and it turns out you would imagine the orbital evolution had happened because there is transfer of mass from one to the other, there is loss of mass from the companion because of the wind outflow and so on. But the rate at which you find these systems evolving is alarmingly larger than that, more than a factor of 10 higher than what would happen because of simple mass loss. Okay. So it looks like most of these sources, the orbital evolution is happening because of tidal interaction between the neutron star and the companion star. These being very close orbits, there is very strong tidal interaction, and that causes the orbit to evolve. And in a few sources where very high rate of orbital evolution was claimed earlier, we have actually corrected those with more accurate measurements. Okay. There are a couple of those sources where earlier projected rates have been lowered by a factor of almost 10 or so. These double compact binaries are of particular interest to us because these are eventual gravitational wave emitters. Okay. When the companion star also goes through a supernova explosion leaving another neutron star, these will be the double compact binaries, and eventually they would merge and produce short gamma ray burst and gravitational wave and so on. Not that we will be there to see them. The evolution time scale is large. In low mass X-ray binaries, where you have matter from a companion star of low mass going to the compact star, you would expect because of mass transfer the orbit to evolve. Okay, so there will be a positive curvature. But here again, the curvature that is measured is at least 10 times larger than what one would expect simply because of mass transfer. Okay. Yeah. So in these sources, we have understood that this is probably because of wind outflow of the accretion disk, and that is measured spectroscopically. While doing this study, we came across one system very, very peculiar. Here, this system, the orbital period does not evolve, I mean, it does not increase, it is actually decreasing. But on top of the decreasing trend, if you look at the data points here, there is an oscillatory pattern. This could be interpreted as there is an extra binary, but there is a third system surrounding it. Okay, there is a circumbinary object, and because of the motion of that around the center of mass of the binary itself is going back and forth. The binary itself is going back and forth, that is giving this oscillatory pattern in the eclipse timing, okay, which can then be converted to determine the mass of the third body and its distance from the binary, okay, which turns out to be about 25 Jupiter masses. Well, if this was true, this happens to be a transient source, it is not observable all the time. When it is observable next time, one should be able to see this oscillatory pattern again. So after our publishing this result, another group studying another outburst of the source actually established that the oscillatory pattern continues. So this object definitely has a third component. We study cyclotron lines, I mentioned. Cyclotron lines, you go through these things quickly. Sometimes it is a discovery of a cyclotron line which allows you to measure the magnetic field strength. We have made very detailed measurements with AstroSat, for example, of cyclotron lines, and we study the spin phases of the cyclotron line parameters, which combined with the polarization measurements that we will have later would help us establish or would help us study the magnetic field configuration of neutron stars in detail. In some sources, cyclotron line you see fundamental and a harmonic, but the fundamental and harmonic energy do not remain constant over the pulse phase and so on. So cyclotron study is one topic that we pursue in detail. I would quickly move on to POLIX after discussing one more topic, which is of superorbital intensity variations. Some of these accretion powered pulsars, in addition to their pulsation, quasi-periodic oscillation, orbital intensity modulation, show a long-term intensity variation, and that has been seen over decades. It is not a transient thing. Hercules X1 has a period of 30 days, 35 days. SMC X1 has a period which is variable between 50 to 60 days. LMC X4 has a period of variation of 30 days, and so on. It is generally understood or believed that the inner accretion disk in these systems is warped by radiation pressure, and that warped structure persists over time. So sometimes you see the neutron star directly, and when this persist structure is towards you, you do not see the neutron star directly, you see the scattered radiation. Okay, that was the general belief, and everybody was happy with that. But then we took up a study of the one such system spectroscopically. If this absorption, if this intensity modulation was because of absorption, that obviously should be far more prominent in low energy band than in hard X-rays. If we study the broadband spectrum of these sources going from a few keV to few tens of keV, one would have expected the X-ray spectrum to fall very rapidly at low energies when the overall intensity goes down. We see no signature of that. One possibility is maybe the absorption is not by photoelectric or neutral material, maybe it is ionized material. We tried fitting this spectrum, set of spectrum with ionized material, ionized absorber as well, assuming that the intrinsic luminosity of the source remains same. This doesn't stand out. Okay. So the prevailing hypothesis that the superorbital intensity variations in these sources is caused by absorption in warped accretion disk structure seems to be not holding. Okay. So these are whole range of X-ray studies that we have been doing over the years. Let me now go on to few minutes on X-ray polarization measurement. So all these studies are X-ray spectroscopic or timing and spectroscopy combined. Okay, and you might think that our plate is full. We could continue doing such studies, maybe go deeper for some sources and so on. But in astronomy of this kind, where data is obtained with an observatory that is made by someone else, and this data is publicly available, or you can write proposals to analyze it and so on, the critical part of the credit actually goes to the observatory. Most of the results that I showed you, if you did not tell me the source name, if you did not tell me the observer, looking at the plot, I would be able to tell you which observatory it has come from. Okay. So in astronomy of this kind, even though data is available, the credit by and large is to the observatory. Okay. This has been possible primarily because the observatory was up there, someone has made it. Okay. So because of that, and because X-ray polarization is practically unexplored. It's only very recently, last year in December, NASA has launched an X-ray polarimeter instrument, and X-ray polarization is really unexplored area. We took up at RRI development of an X-ray polarimeter. There are many processes in astrophysics which should give X-ray polarization, and many kinds of X-ray objects which should give X-ray polarization. So we do expect X-ray polarization to be common in the sky. And polarization measurement in X-rays, one thing is there, you measure only linear polarization, and there is a 180-degree ambiguity. Okay. The instrument that we took up uses Thomson scattering of incoming X-ray photons. There are three ways of measuring polarization. In low energy band, less than 10 keV, it has to be either Bragg reflection from a crystal, or you absorb the X-ray in a gas, the photoelectron that will be emitted will go along the electric field vector. So that is photoelectron, which works in less than 10 keV band or so. In 5 to 50 keV band, it is primarily Thomson scattering, where the scattering will be anisotropic if some of the incident X-ray photons are polarized. And above 30 keV, it can be Compton scattering. Compton scattering polarimeters have an advantage that where the scattering takes place, there will be some energy loss. If you can detect that energy loss as well, you can insist on simultaneity of a photon between of a signal between where it is scattered and where it is absorbed. So insisting on the simultaneity, you can reduce the instrument background by a large factor. Okay, so Compton polarimeters, even though they will detect far fewer photons, are quite sensitive because of this simultaneity. So POLIX has the basic principle is there is a collimator through which X-ray photons will go in. Under the collimator, there is a beryllium scatterer. X-ray photons will get scattered from there. You have detectors surrounding it, but you cannot count on all elements of the detector being identical because you want to measure polarization at a few % level. The signature will be about a tenth of that, and so on. What you want is this whole thing to be spinning around the viewing axis, so that every element of the detector is a polarimeter. Okay, every element would be measuring a modulation in the azimuthal direction. So this instrument we have been working for a long time, from 2006. Around 2012, we came up with. 2009 we made a prototype. 2011 we modified the design and so on. And 2015 we submitted revised proposal to ISRO. And 16 this satellite was approved, for which POLIX is the exposure is the satellite, and POLIX is the main instrument. There is also another instrument called XSPECT, which is a spectrometer, a small instrument on the side of it, looking at the same source simultaneously. POLIX is designed, built, tested at RRI. This is how the raw instrument looks like. You have these 4 detectors surrounding a scatterer. Okay, the electronics is pretty complex, which is again developed at RRI. And satellite has some special requirement that it needs absolute pointing accuracy of about 0.1 degree. It has to be spinning around the viewing axis. We will need very long observations. The flight model is ongoing assembly at RRI. The kind of sources that you would look, primary sources are these accretion powered neutron stars. In spite of so many space missions and observation over wide energy band, hundreds of observations of hundreds of sources. Simple things that we do not know is how is the X-ray beaming pattern from a neutron star? Is it along the magnetic field line or is it perpendicular to the magnetic field, or there is a fan beam type or pencil beam line? How do they switch from fan to pencil? Because we see during outburst the X-ray pulse profile changes. That would come out from observation of sources, polarimetric observations of sources. If you measure polarization at different pulse phases, if the emission is around the beam, then at the peak of the pulse you would expect polarization degree to be low. If it's fan beam, then at the peak of the pulse you would expect polarization degree to be high. Okay. So pulse phase measurements would tell us first thing about the beaming pattern in these sources. As the sources go through a large luminosity change, one would expect the accretion column to change. Okay. Accretion column structure and the beaming pattern to change. So structure of magnetic field, structure of emission pattern, etc. we would be studying with POLIX. POLIX would also study black hole sources, but that's not today's topic. In black hole sources, the main interest is, we know from relativistic iron lines that some black holes are very highly spinning, okay, close to like 0.99, 0.97 of maximum allowed being car. So the accretion disk goes very, very close to the black hole. Okay, and then the X-ray emission which is happening from a corona surrounding the black hole can also get reflected from the accretion disk, and that induces polarization. Okay, so one would expect to see strong energy dependent polarization from accretion powered black holes as well, and the NASA mission would be measuring this in the energy band of about 2 to 8 keV, and POLIX would be measuring in the energy band of 8 keV onwards, 8 to about 30 keV, some brightest sources about up to 50 keV. That is where our interest in black hole sources lie, that this along with the low energy measurements would help us constrain spin up black holes in some of the brightest accretion powered sources. POLIX, as you would understand, a full dedicated satellite and instrument is being built at RRI. So people have worked on this instrument over the years, like 1.5 decades now. There is a very large team. These are the people who are working on POLIX at RRI now, people who have worked at RRI in the past. Shivani from EES has helped us with reviewing our codes and so on. People outside TIF, RRI who have worked on POLIX directly. She's at URSC, Dheeraj Reddy is at TIFR, Santosh has helped us with simulations earlier. We do get very good industrial support for electronics, for various mechanical components and so on. BRC is making the beryllium disk for us, which is kind of the central thing in POLIX from where the scattering happens. So we are looking forward to shift gear now from spectroscopic and temporal studies of various kinds that we have been doing. In the coming years, we look forward to move to polarization studies of neutron stars and black holes. Thank
you. You started saying that you don't work on big questions, but I wanted to ask you, doesn't all of this data that you're collecting for X-rays emission from neutron stars, can that not go into, or will that not be affected by the nature of neutron star equation of state, which is one big problem, right? So in a sense, the data that you collect has to go into any viable model, right? Because or are you saying it's independent
maybe a
of the
little
nature?
indirect way. What matters for us is, for example, where the cyclotron line is formed, we measure some energy of the cyclotron line. The actual magnetic field strength of the neutron star, there is a factor of how much the gravitational redshift is. Okay, that depends on what is the mass radius relation, but we are not directly studying it. So those are kind of in an indirect way linked to this, but not. So neutron star equation of state, I would say, is a grand problem. Okay, in study of neutron star, equation of state is a grand problem.
So, I have a very basic question.
I can hear you. Yeah.
Okay, hi. So I just wanted to ask, see, when you are talking about the POLIX and you are going to be observing the source for a month of that sort. Now, the point is that you are doing a polarization measurement. How stable is the polarization over such a lot? If you're going to be integrating, how stable is the polarization? And when you are going round in an orbit, your actual angle of to the source is also changing. It's not changing too much, but I mean, how good is your pointing going to be? And
these sources are very far away, kiloparsec
Yeah, no,
distance
no,
and so
of
on.
course.
So their angle with respect to where you are in the orbit is that doesn't matter. The intrinsic variability of polarization is a thing, is something one has to keep in mind. 1 month is probably for the fainter among the sources that we will study. Something like 50 millicrab, we will have to wait for a month. If the source is 200 millicrab or 300 millicrab, then a week is good enough. For accretion powered sources, we would not expect accretion powered neutron stars. We would not expect a large dependence or a large change, because it's primarily related to the magnetic field structure, and if the overall luminosity remains same, we would expect the polarization signature to remain same. In black hole sources, one needs to simultaneously know what is the spectral state of the source. For example, black hole sources, the same source sometimes can give this spectrum shown in red and sometimes can this black spectrum. Okay, the spectrum changes dramatically. This is when the emission is dominated by accretion disk. There is a low temperature emission from the disk, and this is when the emission is not dominated by the disk. This may be truncated at a slightly larger distance. It's mostly coronal emission. So one will need to know simultaneously what is the spectral states, and that is where two things. One is this other instrument which is flying together with POLIX would help us. That is the spectrometer. Okay, that will allow us to know the state, and states largely we would know even from the long-term light curve that is available from the all sky monitors, like the MAXI all sky monitor on International Space Station, the Swift BAT telescope on Swift Observatory. So these two give low energy and high energy light curves. Ratio of the low energy high energy light curves would also tell us the spectral states of the source. So that's something we have to keep in mind. Sure. Thank you.
I have a very basic question, because of my ignorance, I guess. So, like, I remember you saying that this POLIX will be about, I think, 400 kilometers from here, right? 400 to 600. 600 kilometers, yeah. And it's a more generic question, like you also have these others, let's say, space-based observatory or even the Mars rovers, etc. So, what is the mode of communication? Like, you will be downloading data, right?
So there is a large onboard data storage.
So
Data that we collect from the instrument is routinely transferred to the satellite onboard memory, and roughly once a day.
So that's through via some intermediate satellite again?
No. Roughly once a day when the satellite is over the ISRO ground station, or communicable from the ISRO ground station, data will be downloaded.
Okay.
Typically once a day.
Okay. And what is the speed usually?
Data download speed, it's in X band, I don't know the exact number, but our data I think will get downloaded in a few minutes. The onboard memory is about 30 gigabits, which can store roughly about 7 days data for POLIX. But we would plan to download data once every day or so.
Let's thank Biswajit once again.